Okay, let's begin with the standard question, which is, do you have any questions? Okay, there was one question which was asked to me on my mail, and I asked not the mail, sorry, in the discussion forum. I did not answer it there because typing out the answer would not really be very easy to do. I wanted to discuss it in class today. But before that, does anybody have any other questions, including on the exam, for example? Okay, if nobody has questions, then let me just quickly flash for you the solutions to the midterm exam, although I'm pretty sure many of you already know how to solve it. The only thing that I want, okay, I'm going to upload this particular file that you are seeing on your screen right now. These are the solutions, actually. You will learn soon. But what I would want to stress for you is this. In the first question, many people have actually found out the right balance conditions, or quote unquote balance conditions. What nobody seems to have realized is that, or not nobody, some of you have, but most of you have failed to realize is that such a balance condition can never be achieved. Basically, because it's insisting that at least one of the components, L, C, R, or whatever, must be negative. Because we are adding a lot of quantities together and getting a zero, which of course is not a possibility. So the answer should have been not just the finding out the balance condition is fine, but the full answer involves being able to say, and that's not obvious from the balance condition itself, that you cannot achieve balance. So am I clear about that? The question actually, if you look at the question, it says, will he be able to get the bridge to balance? And it says, argue whether it is possible to satisfy them. Most of you failed on that last part. You did find the balance conditions correctly. Okay, not all of you, but most of you found the balance condition correctly. But that the balance condition is impossible to achieve is something which should have been obvious, but apparently wasn't. So let me tell you the mark scheme here. If this has 5 marks, so anybody who has got the balance condition right would get 3. And who fails to actually, anybody who achieves the full thing, that is, also argues that you cannot balance it, gets 5. Okay. Any questions about that? Am I still here? I am feeling a bit lost right now. Okay, let's see. You can all hear me, right?
Yes, sir.
Okay. So that was question number 1. That is the only one which was a bit tricky. Because the others, well, the next question I found people make very heavy weather of it, because they made it very, very difficult for many reasons. But the simple thing is, through the inductor and the capacitor, you can simply forget calculating the power, right? There will be no power dissipation on the inductor and the capacitor. They're pure inductor, pure capacitor. And why not? Basically, because remember, one of the results that we derived was this. Power, the average power is given by, sorry, this is the average power that's given by real part of V star I, with or without an extra half, depending on whether you're talking about the actual amplitudes or whether you're talking about RMS values. Here we are talking about RMS values, so this is the formula. But V is Zi, right? So this is always equal to Zi is conjugate times I, so it's actually I mod square, which is always real, times real part of Z. So if a particular impedance is purely imaginary, like an ideal conductor, ideal inductor or an ideal capacitor, you're always going to get 0. Is it okay? So that calculation could have been done much more simply. Many of you have done it, but not all of you. All of you have, some of you have actually wasted quite a lot of time calculating those. Okay, these I'm pretty sure we don't really have much to discuss, except, for example, in this problem, when this voltage is positive, many of you have claimed that both diodes are forward biased. Okay. And I'm not disputing that. That's actually correct. But that this one is forward biased is easy to see. That this one is also forward biased when V is plus 15 volts, that is really not that easy to see. Okay. So I'm not very sure whether those of you just wrote down is forward biased, did it with full amount of thought, or just did it because it seems sort of obvious. So I will urge all of you to think about this problem a bit. Exactly why do you think this diode is also going to be forward biased when V is plus 15 volts? It is. Yes. Just hold on. তোমারই আমি একটু ক্লাস নিচ্ছি, পরে কথা বলবো। সুদিস না একটু কাজ করছি। Okay, so that you have to sort of worry a bit about, because frankly, if I switch this diode to point the other way, it might still seem that the current would flow like this, which is both are fossil forward biased. Whether it's correct or wrong depends on the potential drop, which you have to calculate properly. So most of you didn't do that. Most of you just wrote down that D1, D2 are both forward biased, which in this case was correct, but not really very well justified, because it's not as obvious as it seems. Okay. So that's more or less what I have to say about the medicine. So if you have any questions about the medicine, please go ahead. Okay, none. Fine. So any other questions? That is a no. So, by the way, 2 new videos have been uploaded last week. I'm not very sure many of you have seen that or those. Remember, if you go fall behind, it's going to get even worse later on. It's going to just accumulate and become too much to handle. So I would urge all of you to keep up with what is going on. Frankly, it's actually much lower than what should be the load in the class. So please don't tell me that you are getting too many videos to watch or too many classes to take. There should have been more, actually. But even that, it seems most people are not keeping up with. Half-wave rectifier and negative clippers seem to give similar kind of output. So what is the difference between 2 outputs, or is it the same? Well, Safraj, I would like to tell you one thing. If you look at the video carefully, in that there was some statement about precision rectifiers or precision diodes and actual rectifier circuits. Okay, so there is a difference, but the difference is actually explained there. So please look at that again. I will discuss this again if you still find it confusing. You're right that if you just look at the output, the two sort of looks the same. Okay, but their actual intent and usage is very different. And not only that, so basically, to put it in short, for half-wave rectifiers, what we are really doing is we are creating from a AC, we are creating a DC. That's all we are trying to do. We are trying to get the current to flow in one direction. And frankly, we don't really care much about fidelity. That is, we don't really want to necessarily keep the features of the input sort of intact. Of course, you're not keeping the features of the input intact anyway. You had an AC which you're cutting off. That's true. However, the clipper circuits or the other clipper, clamper, and all those other circuits, they're actually used more for pulse shaping. So you have an input pulse which you want to change in a very precise manner so that from the resulting pulse you can actually sort of do measurements and determine many other important properties. Okay, so typically these are circuits which would be used as pre-processing units connected to measuring devices, and you want to actually reflect the input features as much as possible in the output. So that is why you use different kinds of diodes for them. You use different kinds of circuits which you can connect to them, and so on. So at first sight, the output looks the same, but their behavior and the usage, more importantly, is very different. And that has been explained in the video. So just listen to the part about the precision rectifier or precision diode circuits and rectifier diode circuits. Okay? So that's where I discuss exactly why that is different. So if you still have a confusion after listening to that, we will discuss this in the next class. Okay, anything else? Okay, so one question that was asked in the discussion forum was this. It was about ICEO, so we had basically in a transistor, yeah, the emitter is connected to both base and collector. In the BJT, the emitter is connected to both base and the collector. You mean internally or externally? I'm not very sure. Internally, of course, is not.
Sir, in one of the last lecture that you posted last week, in one of the slides, there was a picture of the BJT in which emitter was one part of it was.
Okay, I'm not very sure I can hear you very clearly, but I think are you referring to this? Are you referring to this kind of a circuit?
No, sir, not that one.
Are you referring to this kind of a circuit diagram or?
No, sir, not the circuit.
No. Sorry, you're just. I'm not sure whether it's my connection or yours because you're just. I can't really make out what you're saying. But okay, let me just put it this way. Okay, I'm trying to guess here about what you're really saying. So let's see. First of all, this is a very crude drawing of what a transistor is like. It of course is nowhere close to that. The emitter is much smaller, the collector is much larger, the base is actually thinnest, and so on. But internally, the emitter, of course, is connected to the base. So is the collector. The base is the only one which is connected to both circuits. Otherwise, not. Okay, right? But you could have a circuit like this. That is emitter could be connected to the collector and
Yes,
to the
sir. It
base.
was the internal connection.
Internal connection is this one. Internal only base is connected to both. This is an external connection we are talking about. Internally, emitter cannot be connected to both. When I say internal, you mean this one or you mean something like this?
No, sir. It was like the base was in three-dimensional,
Oh, you mean this circuit, right?
like. Yes, sir. Yes, sir. Yes.
Mhm.
This
Okay,
one.
okay.
Yes,
Okay,
sir.
so
And
there
another
are
part
also,
of that was like, yeah.
yeah, so there was another piece which was, okay,
Yes,
that
sir.
is a
Yes,
bit
sir.
complicated.
Yes.
So we are not going to describe that here. To understand that, you will have to know a bit more about device physics than we can go into right now, unfortunately. I'm sorry about that. The point is, it's really not connected to the collector. It's connected to something called a substrate. The whole thing is grown on a substrate into which you first grow the collector, then you grow the emitter. Sorry, then you grow the base, then you grow the emitter. And the emitter usually in most designs is put in two such pieces to balance out voltage imbalances, but that is a technical thing that would be difficult to explain at this level. I'm sorry, that would be too difficult to explain right now. Okay, but I now understand what your point is. Okay, so just ignore that for the time being. Just deal with this simple picture that this is the emitter, this is the base, this is the collector. Okay. The fact that the emitter has another part, which is actually not another part, that's looking like another part simply because I'm looking at a section. In 3D, they're actually connected inside. So it's like, basically, it's something like this. A single thing. This is basically done in order to balance voltages when there are no external power sources and so on. Some amount of nifty electrostatics is involved here. So I'm not going to explain that. Okay. Sorry about that, but that's a bit too difficult right now at this stage. That is without doing a detailed analysis of the voltage distribution in a multi-layer junction, which is a rather complicated electrostatics problem. It would be difficult to understand that. So that's the way in which actual circuits, actual chips are made, transistor chips.
Sir,
Yeah, go ahead.
so in a like NPN transistor, like the electrons when they come in from the emitter and then they go into the base and like a few recombinations happen and then it goes into the collector. So the recombinations they represent the base current, right? So
Well, actually, you're right in the sense that those which recombine, they ultimately cause the base current, in the sense that after all, remember every part, the emitter, base, and the collector are overall electrically neutral. But when recombination takes place, say an electron recombines the hole in the base, that portion locally becomes negative, right? If you have a local negative charge somewhere, that charge has to go away. How does it go away? It goes away by ultimately pushing an electron out through the wire connected to the base. Doesn't happen immediately. It's not as if the moment a recombination occurs. So you have this bunch of electrons coming in here, recombining, perhaps one recombines with the base and goes away. So now you have a bit of negative charge here. Okay. So that will actually, this negative charge will essentially migrate to a nearby, to an each another hole nearby. But that will make this negative. So the negative charge will go away from here, this will become negative. Then it will migrate to a nearby location and eat another hole, which means this becomes neutral again, this becomes negative. Ultimately, it will go out through this external wire. So that will produce an electron flowing out or a current flowing in. And this is basically the source of the base current.
Sir, can you repeat again?
So basically, whenever, suppose you, even in a PN junction, say just a simple diode, you have this depletion region, right, in the across this junction. Now, what happens when electron, say it is a PN thing, suppose it's forward bias, an electron flows from here and goes in here. Because of the forward bias, sufficiently many can actually cross the junction, cross this depletion region. But it's not the junction which is the problem. The problem is across the depletion region, there is a repulsive potential. Because of the forward bias, the repulsive potential effect becomes diminished, doesn't go to zero. So not all electrons can cross over, only a small fraction of electrons can cross over. Of course, the fraction increases exponentially with increasing potential. But once the electron goes from here and crosses into here, what happens? It finds itself among a lot of holes. So it's going to just annihilate the hole, right? It will recombine. We don't use annihilate in semiconductor physics, but basically this is in particle physics, we would say electron annihilates the positron. In a similar picture, in the semiconductor physics, we would say the electron recombines with the hole. But if the electron recombines with the hole, what happens to the charge there? Remember one thing. The holes actually may have positive charge, but that doesn't mean that the p side is positively charged, at least not this region. This region is neutral, right? The depletion region is charged. But the outside the depletion region, the semiconductor is neutral. Why is it neutral? Despite having extra holes? Yes? Or so first of all, without any junction, suppose I had just a p-type semiconductor, there's more holes than electrons. Is it electrically charged or electrically neutral?
Neutral.
Why is it neutral? Despite having more holes than electrons?
You said the same amount of holes and
Same amount of?
holes and electron.
No, that would be an intrinsic semiconductor. I'm saying a p-type semiconductor.
Okay.
An intrinsic p-type semiconductor, not intrinsic semiconductor, an extrinsic semiconductor, doped semiconductor, which is p-type. It definitely has more holes than electrons, right?
Positive.
Is it positively charged, or so a piece of p-type semiconductor without any junction or anything? Simple
It
p-type
should be,
semiconductor.
sir, it should be neutral because we are doping with a neutral type, doping a neutral atom with a neutral type. So there shouldn't be any excess of
Okay,
electrons or holes.
Okay, so that's a good point. That's a very good point, because the way you created this was you started with a neutral intrinsic semiconductor, pure semiconductor, doped it with a neutral atom, or not but several neutral atoms. Of course, neutral and neutral cannot give you a charge. That's perfectly true. However, if we just did the calculation in another way, just counted the number of charge carriers, then we see holes are more than electrons. Then how does that get compensated? That extra positive charge due to the hole, how is that compensated?
The extra bound electrons.
Right. Or another way of putting it would be that in order to have a p-type semiconductor, what you really need is, what do you use to get a p-type semiconductor? A trivalent impurity, right? That means that instead of whatever your substrate had, you're putting in something with charge 1 less. So each impurity atom essentially behaves like a negative charge, effectively. Do you get the point? The impurity atom has 1 less positive charge than than silicon or germanium, whatever the intrinsic semiconductor is, because it's trivalent. And for n-type semiconductors, the same thing happens. You have more electrons, but you also have an extra positive charge because you have pentavalent impurity which is sitting there instead of a quadrivalent silicon or germanium. Okay, so it's basically the dopant at ions which they are no longer atoms. They were atoms when they came in, but once they come in, they become ions. Okay, and these because they either give up the extra electron or take in an extra electron, whichever way. But basically, you have an effective negative charge for a dopant trivalent impurity in a p-type, and an effective positive charge for a dopant pentavalent impurity in the n-type. Okay. Now, the whole important thing about p-n junctions, that is something I stressed quite thoroughly, I guess, I hope, in the video on the p-n junction, is that the major important point about this is charge carriers can move, but the things which maintain charge neutrality, that is, these trivalent atoms and these trivalent atoms or pentavalent dopant atoms, they can't move. Okay, they will not be able to cross. So, which is basically why in the immediate vicinity of the junction, that the charge carriers move away. That is, electrons and holes move away. Okay, electrons from the n side, holes from the p side. But the dopant impurities stay where they are, which is why here you have the dopant. Earlier, what was happening? You had dopant impurities, your charge carriers. Both were cancelling each other out. Now, from here, the charge carriers have gone away. Dopant impurities are still left. So, which is why in the p-type, in the depletion region on the p side, you have negative charges because the dopant impurities are left, are still there, and the holes have left. On the other hand, on the n side, the dopant impurities have plus charges, so they are also left there, which is why you have a potential difference. You have this barrier across the junction and so on. All of this happens because of that. Okay, so basically, it's an interplay of the charges which can move and the charges which can't move. The charges which can't move are also very important in this because they are the ones which produce the barrier potential. Okay. Now, here, suppose in a p-n junction, an electron from here, I've given enough forward bias, it can cross this region, it gets in here. Now, here you still have holes. So what happens is this will almost immediately meet a hole and recombine. So this goes away. But that would mean what? Here remember here, there is no charge neutrality because holes have left, dopant impurities are behind. Here on the other hand, you had holes and dopant impurities in equal numbers. So this region was neutral. Now one hole has gone away. So what will happen to this region? When the hole goes away, what happens to charge here? So let me repeat once again. If I look at the p-type, p side only, let's say for the time being, you have the depletion region where you have Dopant impurities, no holes. So this is negatively charged. Here, you have on this side, you have holes and dopant impurities. So this is neutral. Similar thing happens on the inside. Let's not repeat because that's the same thing. Now an electron from this side crosses over here, recombines with a hole which is present here. So what happens to charge locally here? Earlier you had this hole, you also had a dopant impurity, and that made the whole thing neutral. Now what will happen? Yes? Yeah, Madhav is saying negative charge. Of course, that's what is going to happen. This region is going to become negatively charged. But if a region becomes negatively charged, it's going to pull holes from the vicinity into here. So what will happen is again it will recombine, but this region will become negative because the hole here has gone away. Right? So then other hole from here might migrate here because of the fact that this is negative now. Then this will become negative. So this basically, the holes will keep on drifting around until a hole actually pulls in an electron from the external wire. So there's a wire connected to this, and electron will flow in from that wire. So an electron will flow in, and you will have a current flowing out. So that's basically how currents develop. Recombination causes currents. Okay? Clear? Does not cause current immediately. That is, in the NPN transistor, whatever recombination happens at the base does not immediately give rise to the base current, but that is the cause of the base current. That much is right. So is this clear, or does it need any further explanation? Basically, local okay, so basically what you have to realize is that this entire game is one of trying to balance out charges. If you have a local potential and if you have charge carriers which can flow around it, it's going to try to flow to neutralize that potential. That's essentially what is going to cause all these currents. Okay. So if you come to the transistor, a very similar thing happens. Well, similar, but it isn't different because the forward bias in the base emitted junction causes a huge amount of electrons to enter here. But they don't get to recombine. At least most of them don't get to recombine. Why? Why don't they get to recombine? Okay, one answer is because there's a reverse bias in the collector base junction. The reverse bias actually should have prevented current from flowing from between collector, or at least reduced current flowing from collector to base. However, here what's happening is because of this injection current, huge amount of electrons have entered into the base, and most of them are going to be swept to the collector. That much is right, but there are other contributing factors as well. The base is deliberately kept very, very thin so that the electrons spend a very little time in the base. You understand that? If it's thin, it's just going to be swept across very rapidly. Also, the base is very lightly doped, so there are very few holes in the base to recombine. Okay, so vast majority of the current which goes from the emitter into the base gets swept across to the collector because of the reverse bias in the collector base junction, but primarily also because the base is so thin and so lightly doped. But the very small amount which recombine, some do recombine, and those recombinations, of course, cause charge imbalance in the base by the same method as before, and that will ultimately lead to the base current. Again, so every electron which recombines contributes 1 electron to the base current. But that's not the same electron, of course. It's an entirely different electron, but effectively, in the long run, although in the long run is a very wrong word to use here, because here long run means nanoseconds or less. Not even nanoseconds, picoseconds or less. Once the electron recombines with a hole in the base, an electron gets pushed out from the base wire, creating a positive current going in. Is that clear? Any further questions? Okay, so I will finish today's class with the question which is very related to this one. That was a question in the discussion forum, which is actually an interesting and important question. It's about ICBO, or actually it's not about ICBO, it's actually about ICEO. ICBO is current from base to collector or collector to base, depending on whether you are NPN or PNP. And the O means with emitter open. That means you have not connected the emitter to anything. So basically the emitter base junction is really not in the game at all. The collector base junction is like a reverse bias diode now. There is no emitter base connection. The collector base junction is just a reverse bias diode. Okay. And because it's just a reverse bias diode, there will be very little current flowing through the collector base junction. There will be some, and that some is basically because of the fact that even in reverse bias, some current flows through the diode because of bond breaking, thermal effects, and so on. This current, of course, strongly depends on the temperature. If the temperature is high, you are going to get a lot of current. Okay. Well, lot is relative, but still you are going to get a lot of current, lot more current if the temperature is higher than if the temperature is low. Is that okay? So that's pretty straightforward. That's just the minority carrier current which flows between two elements which are connected in reverse bias. So nothing very surprising about that. ICEO, on the other hand, is current from collector to emitter. With base open. So now there is no connection in the base, right? So the current, you have connected the emitter and the collector with the battery, perhaps. The base is open, there is no connection. And so now you're asking what kind of voltage you are going to get. Now, what kind of current you are going to get? Notice that because of bond breaking, you will still get okay, so let's put it this way. Okay, let me use rather artificial numbers. But let's say in usual operation, let's just say 100 electrons go in. Suppose this was, you had a positive bias in the emitter, 100 electrons going in, and you had a base collector connection. So 100 electrons going in, let's say 99 will go through here, one recombination. That's a typical kind of fraction that happens. Out of every 100 electrons which go in from the emitter to the base, which are injected, 1 electron recombines, and the rest 99 goes to. That would give an alpha of 0.99 or a beta of 99, which is actually reasonably small. Most transistors are better beta than that. But now, suppose I don't have any injection current. I do have a connection, but I'm not trying to force current to flow in. But what is going to happen is, because of the fact that there is a reverse bias here, minority carriers will flow in. Okay? Now, when minority carriers flow in here, that is, minority carriers meaning, remember this is NPN. So now, when a minority carrier flows in here, what happens? There's a recombination in the base as before. Now, if a recombination occurs, or even if it doesn't, you have excess speed, right? Because remember, minority carrier means what? On the inside, you have some piece which will be flowing in across the junction, because that's going to be helped by the reverse bias. So the hole from the inside has crossed over here. That will produce a positive charge here, right? And a positive charge is locally or rated. What will happen? It's going to pull in electrons from the emitter in order to cancel this hole's positive charge, right? Is it okay? Because electrons are there only in the emitter side. And the emitter is going to now contribute electrons, which comes into the base and cancels out the hole. Remember, if you had a wire here, what would happen is, once the positive charge comes in here, electrons would have flown in through the base wire. But now the base is open. Electrons can't flow in through the base wire. Is that clear? So that route is out. So electrons have to come in from the emitter into the base. But now what happens? In order to cancel out this one hole, how many electrons do you need from the emitter? Remember, collector to base still has a reverse bias. This extra one hole which has come in from the collector to the base, that needs to be cancelled. How many electrons do you think are needed for that? To cancel this one hole. Yes? Come on, give me a guess. Is it 1 or 100? Is this not making sense at all? Just from your responses, I can't really make out whether I am making sense or I'm not making sense at all. So if I'm not making sense, please tell me. Then I will try repeating this.
Could you just repeat the question again?
No, the question essentially was this. You have a reverse, suppose you don't have a base wire connecting it. So base is open. Okay. There is one hole which one of the minority carriers, this hole from the inside has crossed over to the base, which will happen because of the minority carrier current. Okay, it's a tiny current only one hole right now. It just crossed over here. But once it has crossed over, that's an extra hole. And that means extra hole meaning one more hole than there was already. So there's an extra positive charge. And positive charge or negative charge in locally will have to be neutralized. Okay. So how is it going to be neutralized? By pulling in electrons from somewhere. Now, if the base wire had been connected, then ultimately the electron would have come in from the base wire. Okay. From the external circuit through the base wire into the base. That's what would have happened if the base wire had been connected. Now, because the base wire is not connected, remember we are talking of base open. If this happens, then no current will flow in from here. So where can the electron come from? The electron can only come from the emitter. Questions: how many electrons do you need to come in from the emitter?
One electron should neutralize one hole.
Right. That's good. One electron should neutralize one hole. But the question is, how many should come in? You are right. One electron. But remember, there's this base collector reverse bias, right? Which means most of the electrons which come in from the emitter into the base, they get swept right across into the collector. Okay. Remember, we said out of 100 electrons which came in, which were injected from the emitter to the base, 99 went through, only one recombined. So this hole has to recombine with an electron which is coming in from the emitter. So how many electrons must come in from the emitter?
If the ratio is 100:1, then 100 electrons should be coming.
Right. If the ratio, that's just a fictitious number, it's close to the actual number, but the actual number may differ. But you're right. In order to neutralize this one hole, 100 electrons must come in from the emitter. And as a result, what happens? Where do these 100 electrons go? One neutralizes the hole, the other 99 goes through, which means the total current that you get. So one hole crossing over across the junction, which is basically why you have this tiny ICBO, leads to 100 electrons going this way. Not 100, but 99 electrons going this way. Okay. So you get a total current which is much, much larger than that would have happened because of the minority carrier current, roughly 100 times larger. Okay. Which is why ICEO is much, much bigger than ICBO. At the heart of ICEO, there is ICBO, in the sense that ICBO is this minority carrier current. If suppose there had been nothing here, the emitter had been disconnected, and you had a reverse bias here with a wire connected, hole comes in, an electron moves in through the wire to compensate. So for every hole which drifts into the P side, you get one electron moving in. So that's the current, ICBO. But without this junction in place, without this connection, or without any current flowing in through this, electrons will have to come in from the emitter, and many more electrons will have to come in than needed to just recombine, simply because most of them will be swept out. Do I make myself clear? So instead of a very small, very, very tiny current, because of minority carriers, you get a reasonably larger current. Okay, remember, you're starting with a very tiny current. So even 100 times bigger current is still very tiny, but it's 100 times bigger at least. That's something you have to keep in mind. Okay. And what is drastically important is the fact that ICBO is a minority carrier current. Of course, it increases with the number of minority carriers. Minority carriers are created by bond breaking, that is basically by temperature. So larger the temperature, larger the ICBO. Okay, and it actually increases exponentially with temperature. And it's ICEO, which is also proportional to ICBO. So it's going to increase drastically with temperature as well. Okay. Okay, let me just take a look at the. Okay, Amitesh, sorry I didn't see your message before. Okay. Tomorrow we will have a class at 2 o'clock. And tomorrow I will start with Amitesh's question. This voltage reply, I missed that. Sorry. Okay, so let's call it a day today. Tomorrow we will start at 2 and we will start with the voltage tripler, because I think Amitesh had asked this in a class before also. I just somehow missed that.